All right. Hi, guys. Can you see me and hear me okay? All right. Thank you for the thumbs up. Okay, so today we are going to jump in to finish off chapter 4, the stuff we didn't get to last time. Time willing, I'm going to give you guys a little flavor of what's coming in chapter 5, but I'm going to stop lecturing at 1:25 p.m. today and let you guys start in on quiz number 3. So that's how this is going to go. So first there's going to be lecture portion, and then I will release you guys. You'll log out of Canvas, you'll log out of your browser, you'll log into the Respondus browser and take quiz number 3 through Canvas. Okay, so to get us started, as I said, we're almost done with chapter 4. There was just a little touch of chapter 4 that we did not cover in class on Monday. This last bit, reactive intermediates, is not on today's quiz. I promised you on Monday that chapter 4 will be on the quiz, but it will only be the material that we covered through class on Monday. And you do not need to come back to the Zoom class after you take the quiz at 1:25. When I release you guys to go take the quiz, you can log off of Zoom and we won't reconvene together again until Friday at 1 o'clock. Okay, so today what we're going to do, as I said, is finish off chapter 4. I'm going to give you a little bit of a flavor of chapter 5. And then we will take the quiz. And yes, for the quiz, it is going to mostly cover chapter 4. There's 8 questions that are from chapter 4. And there will be also 2 questions that are from chapter 3. But again, this is only the material after exam 1. You will need the Respondus lockdown browser for the quiz. This is going to be true for every assessment from here on out. We didn't have time to set it up for the first quiz, but if you guys remember, it was set up for the second quiz as an open book to make sure everybody had their Respondus loaded and ready to go. And then the exam 1 had the Respondus browser, and pretty much every assessment from here on out, you can assume that you will need Respondus. So not the camera part of Respondus, just the regular part of Respondus. Okay. So let's go ahead and chop off the end of chapter 4. The end of chapter 4 has to do with reactive carbon intermediates. And there are really 4 different species that we are going to talk about. And the main 2 for this course are the 2 on the left, carbocation and radical. We'll see a little bit of carbanions towards the end of the semester. And really for this last one on the far right called carbenes, we will see that today, and then you won't ever really see it again. And it might pop up once or twice, but this 4th one is really here for kind of completeness sake. But these 2 on the far left are the most important. So what am I talking about when I say reactive intermediates? Well, they're short-lived species, right? So they're high in energy, they're reactive, and they are, all of these, if you look at them structurally, and if you think about our chapter 1 fundamentals, you can see that all 4 of these have reasons that they might be unstable, right? So the carbocation and the carbanion, both of these have formal charges on carbon. And so that's less than ideal to have anything with a formal charge. Notice also in the carbocation that carbon only has 6 electrons, so it does not have a full octet. With the radical and the carbene, there are no formal charges. But if you look closely, this carbene, that carbon also only has 6 electrons, right? 4 in bonds plus 2 lone pair. And the radical only has 7 electrons. So most of these, with the exception of the carbanion, most of these are missing their full octet. That helps to create an instability in them. And the carbanion, which does have a full octet, carries a negative formal charge on carbon, and carbon is fairly electropositive. So you can see, using our fundamental information from chapter 1, you can see why each of these 4 types of things are considered reactive intermediates. So now I've shown you the examples here based on methane, so a methyl group base for these reactive intermediates, but these other substituents here don't all have to be hydrogen atoms. They could be other carbon atoms or whatever the rest of the structure is. The key part here is looking at what's going on with the carbon at each of these reactive intermediates. So we'll talk about each one in a little bit more depth, starting with carbocations. The carbocation structure, as you can imagine, is sp2 hybridized. It's planar. And the reason for that is because it has to accommodate only the 3 bonds. So for Vesper theory, we only have 3 things that we're trying to, 3 electron pairs that are trying to repel each other, right? And so the empty, there's one unhybridized p orbital that's left over, and that vacant p orbital is where the positive charge resides. That's where that formal charge kind of exists. So this is an empty orbital that is just waiting to take on some electrons, right? So there's a name for that. Can you guys think of the name for that? This empty orbital that is just waiting to take on some electrons? It's not a nucleophile, but it's an electrophile, right? So this empty p orbital counts as an electrophile because it wants to get some electrons. It also counts as a Lewis acid for those same reasons. Okay, so our carbocations are planar, empty p orbital here, sp2 hybridized. We can also think about what happens when we begin. So the examples I've shown you all have 3 CH bonds coming off of that carbocation, but the stability of this carbocation is impacted by what these substituents are. And as soon as you start making these substituents not hydrogen atoms, you get an increase in stability. So this methyl cation is the one we were just looking at. If you swap out one of the hydrogens for an R group, you get a primary carbocation, right? Primary because that carbon is attached to one group that's not a hydrogen. If you add in, keep on adding in, you get a secondary carbocation and a tertiary carbocation. The more substitution you put on that carbon, the more stable it is. So let me say that again. The more substitution you have on that carbon for a carbocation, the more stable it is. We saw this already with carbon radicals. So it's the same trend for carbocations and for carbon radicals. And now I'm going to show you why that is. There's two different actions at play here. The first is called an inductive effect. So it's very, very small, but the polarity of this carbon-carbon bond is pointing towards this carbon just ever so slightly a little bit, because the hydrogens over here versus the carbons over here help to provide that bond polarity. The more useful thing actually is to think about what the bond polarity would be like for carbon-carbon, which is pretty well neutral, versus carbon-hydrogen, which that hydrogen is going to be more electropositive. So one thing that we can say here is that the electron density through an inductive effect means that we will be donating extra electron density towards this carbon through an inductive effect. The more important feature here, and the one that's a little bit actually, I think, easier to see, is something called hyperconjugation. In hyperconjugation, what happens is that if you have a substituent on that carbocation, no matter what that substituent is, if it's not hydrogen, it will have another bond coming off of it, right? So if it's a methyl group or if it's a carbon chain or anything else, it would have another group coming off of it. And so in the case of a methyl group, you can see the sigma bond between a neighboring carbon and its hydrogen can actually have a little bit of overlap with the electron density of that sigma bond on the neighboring carbon with the empty p orbital, and that will help to stabilize it just a little bit. So you can imagine this is called hyperconjugation. You can imagine how if you put one methyl group on, this helps a little bit, and then if you put a second methyl group on, it would help a little bit from this side, and a third methyl group would help a little bit from that side. So this hyperconjugation, for me personally, really helps to explain why the more substituted carbocations are more stable. So the other possibility for providing extra stabilization to carbocations is when the carbocation exists directly next to a pi bond. So this has a special name. Always, if you have a pi bond, the carbon, the carbon next door is always called the allylic position. And so if you have an allylic carbocation or a carbocation at the allylic position, meaning directly next to a pi bond, then you can actually draw a resonance structure. If you think about what this pi bond is, that pi bond is two unhybridized p orbitals that are parallel with each other that have two electrons in them. And if you think about what your carbocation is, it's another unhybridized p orbital. And if you line it up with the p orbitals of the pi bond, then you can move the electrons around covering all three of these atoms. So you can put them between these two carbons, or you can put them between these two carbons. And so we can see through allylic carbocation resonance stabilization that this allylic carbocation is more stable. And you can see also, if you do the sort of the average of these allylic positions, you can see how there's ends up being a delta positive on both of the end carbons of this sequence of 3 carbons that have the p orbitals. Okay, so that covers it for carbocations. Next, I'm going to talk about radicals. Radicals track almost perfectly with carbocations. So if you've understood and remember everything I just said about carbocations, we're going to take the same concepts, same exact concepts, same trends, same reasonings, and we are going to apply them to radicals. So just like for carbocations, carbon radicals are going to be sp2 hybridized. If you think about VSEPR, VSEPR, it's valence shell electron pair repulsion. And so here our radical is not an electron pair, it's a single radical. And so it is allowed to hang out in this p orbital unhybridized still. So for our carbon radicals, we will have one unhybridized p orbital, and the other 3 orbitals will hybridize to be sp2 hybridized. Just like we saw with carbocations, there's added stabilization every time you swap out a hydrogen for a carbon and the things attached to the carbon. And so we have the same order of stability as we do for carbocations. Here is the same thing I just said in a more drawn out fashion, where the most stable carbon radical is the one with the most R groups on it. This is a tertiary carbon radical. Here's a secondary carbon radical, it's a little bit less stable. And then of course the least stable is a methyl group. And the same reasons and rationales that applied for why the carbocations were more stable when they were more substituted, same rules apply here for these radicals. Also, just like carbocations, you can have an allylic radical, meaning your unpaired electron lives in the carbon next to a pi bond at the allylic position. So these allylic radicals can also be stabilized by resonance, and you can distribute that unpaired electron across these 3 carbons, giving it that extra stabilization. This is called resonance delocalization. That term can apply to carbocations also, and it's really helpful in providing extra stability, and we'll see that coming up in future chapters. Okay, so we've covered carbocations and carbon radicals. They all track with each other. Next, we have to go to carbanions, and these carbanions are going to be completely opposite from everything that we've seen so far, right? Now we have a pair of electrons in our orbital, which means it's going to follow VSEPR, and we have to account for the repulsion of this pair against all of the other pairs in our bonds. So that means that now we need to pull in our 4th orbital to our hybridization scheme, and carbanions are going to be sp3 hybridized, right? They're going to be sp3 hybridized. They've got 6 electrons in bonding pairs and then a lone pair. As you can imagine, carbon is not that electronegative, right? It's one of the more electropositive elements, especially of the ones that we deal with. So it is not happy. It is unstable because it's carrying this negative charge. That's going to make a carbanion highly nucleophilic and highly basic. This lone pair is going to want to go do a reaction. It's going to want to either find an electrophile to form a new bond, or it's going to want to find a proton and act as a base to abstract a proton. The stability of carbanions is also reversed from carbocations and carbon radicals, and kind of for the same reason. So now the same sorts of things apply, where as you have higher substituent levels, you'll have more electron density, but because there's already a lone pair in that fourth orbital, that added electron density is now destabilizing instead of stabilizing. So the more substituents you put on a carbanion, the lower the stability goes. This is, again, the opposite trend than for carbocations and carbon radicals. And the last thing I want to note about carbanions is just to kind of drive home the point of how basic and how nucleophilic they are. So you can go back to your chapter 2 and look at pKa charts for hydrocarbons versus other things, and you'll see, and we talked about it at the time, a carbanion is the deprotonated version of a hydrocarbon, right? And those have really high pKa's, like in the 40s, sometimes even in the 50s. So these high pKa's for the conjugate acids of what we're talking about mean that these are very, very, very strong bases. And in fact, they're strong enough to remove a proton from ammonia, which already has a lone pair, giving something that looks like this, which kind of looks crazy, but it's actually more stable, right? Because this nitrogen has a full octet, and now our nitrogen is carrying the formal negative charge, and nitrogen is more electronegative than carbon. Okay, and then finally, our very last reactive intermediate is called carbenes. And as I mentioned when I was kind of introducing all 4 of our reactive intermediates, we are not really going to deal with carbenes in this course. I'm going to show them to you here so you know what they are, kind of for completeness sake, because they're one of the 4 types of reactive carbon intermediates. But you don't really have to worry about the reactivity of carbenes for this class. They may come up later in second semester. I can't actually even remember whether or not they do, but focus your attention on the other 3 first. And once you have those down, think about carbenes. Carbenes are weird. They're very weird. They only have 6 electrons. So they have both a lone pair and an empty p orbital. Okay, so these are very strange creatures, these carbenes. If you do your formal charge calculation, you'll see that that carbon has no formal charge. It has a formal charge of 0. But you can imagine it's carrying now a lone pair of electrons in one hybridized orbital, and then it has an empty unhybridized orbital. So this lone pair of electrons can act as a nucleophilic component to the molecule. This empty p orbital can act as an electrophilic component to the molecule. So all of this is to say that carbenes have very unusual reactivity, and they can react in a lot of different ways. They're only 6 electrons, right? So they're definitely reactive intermediates. And that's literally all I'm going to say about carbenes for this course. Your book has a chart. I've put the same chart up here just to summarize everything that we've said. Carbocations and carbon radicals, these things are going to track with each other in terms of stability. More substituted is more stable, right? And these can, the carbocations are highly electrophilic and are able to kind of receive electrons into that empty p orbital. We didn't talk much about it here, but they also happen to be strong acids. Don't worry too much about that. We'll see it come up later on. Anions have the reverse stability trend, where as you add in,
this is my deal.
As you add in more substituents on your carbanion, you reduce the stability. So carbanions are becoming less stable the more substituents you have. They're strongly basic and strongly nucleophilic. And then finally, the weirdo carbenes, which can be both nucleophilic and electrophilic. Again, don't worry about those too much for now. Make sure you focus on these 3, and mostly on these 2 for the next couple of chapters. Okay, so I have just a couple of minutes, just 4 more minutes that I'm going to keep you guys here. And I just want to give you kind of a flavor of what's coming in chapter 5. So for Friday's class, we're going to spend most of our time covering chapter 5 and give you guys some food for thought for over spring break. Chapter 5 is going to introduce a new way of thinking and looking about molecules that's going to really kind of push your boundaries and push your limits in terms of thinking in 3 dimensions. So I just want everybody to kind of be prepared and primed for that and ready for that. So I'm going to go ahead and give you kind of a little flavor of that in my last couple of minutes here. So I'm going to bring you guys first all the way back to chapter 1, where I first introduced isomers. And just a reminder, isomers are going to be molecules that have the same molecular formula, but they differ in the arrangement of their atoms. And I just want to point out, because a lot of people struggled with this on the exam, if you are just rotating around bonds to convert one structure to the other, and remember there's free rotation around most sigma bonds, when you rotate those bonds around each other, you are not changing the bonding order or the bonding pattern or where things are spatially relative to each other. You're just rotating around a bond. So this compound that I'm showing you on the left and this one that I'm showing you on the right, they're actually the same compound. These are not isomers of each other because they're the same molecule, because you can just rotate directly around that sigma-sigma bond. Okay. You guys, I know you're starting to ask questions in the chat box about the quiz, but I told you I was going to lecture until 1:25. So at 1:25, I'm going to release you and you'll have 25 minutes. I haven't changed the time that it releases for the quiz yet because I didn't want you guys missing out on the lecture and leaving the lecture early to take the quiz. So I'm going to release you at 1:25 and the quiz will open actually at 1:25. Okay? So I got just 2 more minutes and I'd like to keep everybody's attention on the chapter 5 material for these 2 minutes. Okay, so recall isomers. These are the same molecule because all we did is rotate around a sigma bond. Constitutional isomers are going to differ in their bonding pattern. We also talked about stereoisomers. So these are the 2 different types of isomers that we introduced in chapter 1. And I told you in chapter 1, the type of stereoisomer I introduced was called cis and trans. We applied it both to pi bonds and to rings. But I told you we would learn a whole set of new types of stereoisomers in a future chapter. And now we're here. So the one that I'm going to be introducing to you guys on Friday is called enantiomers. And we'll spend more time on Friday talking about this, but I want to introduce them here just to give you guys a flavor of what's coming. These enantiomers are going to be defined as compounds that are mirror images of each other, but are not superimposable. So what do I mean by that? What I mean is that you can take a molecule and you can draw out the mirror image. So you can see if this is a mirror plane, we're going to reflect perfectly through the mirror. So this orange atom is coming forward, this gray atom is going in the back. You can look at these molecules and you can see that because of the 3-dimensionality to these with the wedge and the dash, you cannot overlay these. If you try to overlay this carbon-methyl bond with this carbon-methyl bond, even if you rotate around this bond to get, for example, the hydrogen atoms overlapping with each other, the 2 other substituents would be not overlapping correctly. So a lot of times you can call this a handedness, and you can look at your right hand and your left hand, which are mirror images of each other or close to it, but you cannot superimpose them on each other. So that's where I'm going to stop now. Thank you guys for your patience and attention in these last couple of minutes. You guys can leave Zoom now, and what you're going to need to do is log out of Canvas, log out of Zoom, log in with the Respondus browser, log back into Canvas, and then you'll be able to access the quiz under assignments. Okay, so I'll stick around here for a couple of minutes in case anybody has any question.